This is Dr. Wood with Citadel Civil Engineering. This is CIVL203 Dynamics, Learning Objective 2.4. In this lecture, we're going to introduce curvilinear motion and set ourselves up for our next three videos looking at three different coordinate systems that we can analyze curvilinear motion in. This is Chapter 11.4 and 5 of your Beer and Johnson textbook. We're still looking at particle kinematics. So as we think about curvilinear motion, we're going to be modeling bodies as just a point with a mass and tracking its motion. That's all we're worried about with kinematics, is that geometry of motion. And so we'll remember that when we talked about curvilinear motion, we said that rectilinear motion, we compared these two, and now we're going to be looking at curvilinear motion. And curvilinear motion is going to be in 2 dimensions in this class. It could be in 3 dimensions, and your textbook has a nice 3D section as well, where we're going to have a curved path. Everything we're doing is going to have to be in vector notation, because now we have a sundry of directions that can happen, and then we can talk about things being scalar along the path. Okay, so curvilinear motion, this is what we're looking at. And it works out to be really nice. Now, the example I want to use to help us think about this is this roller coaster. So I'm from Texas. I grew up in Dallas. This is a classic, iconic roller coaster at Six Flags Over Texas in the Dallas-Fort Worth area. The Judge Roy's Scream. It's nice because it has a nice profile to it. So what we're going to look at is the initial curve. And so if we were interested in considering where this curve was and thinking about the points along that curve, we would talk about exactly the same properties that we've discussed before. So when we think about our curvilinear motion, we'd want to start with position. Where is the car on the path? And we're going to have that position vector, r, now with a very clear vector hat, as a function of time. So this is position as a function of time. Okay. So a function of time there. It's going to be measured from the origin typically. And that origin can be established arbitrarily depending on our needs. And it's going to be expressed in orthogonal components. What this means is that each component of our vector is going to have x and y components to it. So if we think about this position vector, it's got some distance x and some distance y acting on it. And that's going to lead us to be able to use the Pythagorean theorem to measure the magnitude. So when we look at the magnitude, the total distance, we're going to use Pythagorean theorem, and in 2D, that just means x squared plus y squared. So the coordinate locations. There are multiple orthogonal systems. This assumes Cartesian coordinate vectors. We're also going to talk about the orthogonal system associated with path and tangential or path coordinate systems, and then polar coordinate systems. So we have that to look forward to. There's our magnitude. Our units, as before, were meters or feet. So that hasn't changed. But typically we're going to think of this as an IJK or other unit vectors to define this. Now, when we go from the position, it's one thing to know where it is. We might also think about how fast it's going. So that would start us along the path of thinking about velocity. Velocity. And the velocity, v, as we've actually talked about before, is equal to dr dt. So we're going to look at this change, and so you can see that the vector there is changing. We actually get a delta r going on there. And if we take the limit with respect to time, we're going to find that we get some velocity here, like so. Now the thing about velocity is that it's always tangent to the path. So it's always going to be tangential to the path. It's always going to point in the direction of motion. And so if we think about this, makes sense when we're on a roller coaster or we're in a car, that we're used to looking forward as the direction we're going, unless we're doing something crazy, right? So looking forward, the direction we're going, our velocity is tangent to the path. And then this is also illustrated by vector mathematics. And so the magnitude or the speed is going to be equal to, again, Pythagorean theorem, but now looking at the x and y components of the velocity. So that's kind of what we're thinking about there. So we got position and we've got velocity. Now the thing that's interesting about this is that when we do this derivative, we also have to take derivatives of the direction components. So not only is it the magnitude in the x and y direction that we're looking at here, but it's also going to be the derivative of the I or J or the equivalent unit vector depending on our system of units that we're working with. So that math gets a little nasty, but it's in your textbook, and then we'll just jump straight to the answer, which is in your FE reference handbook, and will be in your notes once you've watched these videos. All right, so we got that there. Our units will be the same as they were in rectilinear motion, so meters per second or feet per second as we go through that. So it's tangent to the path. So hopefully that's clear so far. Now, if we want to go to acceleration, we have to look at the hodograph. Now, we're not going to use the hodograph very often, so there's no need to panic, but it's basically just a plot of the velocity space going forward. And so when we look at the hodograph, we see that our velocity may change, and it can change not only magnitude, but also direction. And so because the magnitude and the direction are changing, we can get to the point where we find our acceleration. Okay. So our acceleration is also typically thought of as a function of time. It's going to be equal to dv dt, like so. Okay. Now this is not going to be tangent to the path. It's tangent to the hodograph. Y'all should say hodograph. It's a funny word. Hodograph. And that's okay. We're not going to use it very often. And the reason it's not tangent to the path is typically what we'll end up with is an acceleration that is, part of it is along the path, and that's going to be changing the magnitude, so the speed. So if you press the accelerator, you can change how big the speed is, right, on your car. So that's the portion of the acceleration in the direction of the velocity. And then there's going to be a portion of the acceleration that's perpendicular to the velocity. And that perpendicular component is changing the direction of the velocity. Remember, this is the change of velocity with respect to time. So we're going to have a change in the velocity, both possibly in its magnitude and in its direction. And so by changing the direction, we've got that normal component to the path that's engaging there. Now, magnitude, same as before, because the system we're working in is orthogonal, the magnitude of the acceleration is going to be the square root of the sum of the squares. So we're going to get good at that. And our units will be just what they were before, meters per second squared and feet per second squared. And so in this case, we can see where the acceleration, because the roller coaster is now going up, the velocity is decreasing. There's a little bit of the acceleration that's pointing backward from the velocity, right? So if we look at that there, right, it's pointing backward in the direction of the velocity. And then there's part of it that is normal, that's causing the velocity to turn upward because we're going up the roller coaster. So we're turning up, so we're getting a change in direction, and then we're slowing down a little bit as we go up this hill here. So we're losing some speed. So that combined means that our acceleration isn't necessarily tangential to the path. So that's sort of the thing that we're looking at there. Finally, if we think about our procedure, it's going to be the same as it was before in rectilinear. It's It's just our diagrams are going to be more important because the work we're doing is more complicated. There's multiple dimensions going on. So we're going to start with our kinematic property diagram where we sketch position, velocity, and acceleration. And then we would write our kinematic relationship equations, which we have the base form of here. But again, everything we've done in rectilinear is going to have a similar corollary in curvilinear. And then from there, hopefully we're able to solve for our unknowns. So I hope you're seeing the pattern that in engineering analysis, we're typically going to draw a picture, make sure that mental model makes sense. We're going to write our kinematic relationship equations, and then we're going to solve for the unknowns. That's what we have so far. And the next section will actually get into particular coordinate systems. Thanks.